Hello, welcome everyone. We're so happy to kick off our spring 2022 speaker series. So I have just kind of a few comments or housekeeping, if you will, before we get started here. As we work towards better inclusive practices here at IBS, I have a few brief reminders. We will be using the chat and raise hand features for clarifying questions during the presentation, but please hold other questions until the end. We have enabled subtitles and the ability to view a live transcript. If you utilize the CC button at the bottom of the screen, you can view the live transcript or turn on or off the subtitles if needed. I wanted to note that we are recording this meeting. We appreciate being able to see each other, so if you would like to have your camera on, you're welcome to do so. However, we also acknowledge that Zoom fatigue is real and there are other reasons why people may not want to have their cameras on, so you are also welcome to keep that off. If you would like to rename yourself to include pronouns, please do so. And if you need help with that, you can chat with me privately and I can assist. I would like to take this moment to read our land acknowledgement before we get started. Acknowledging that we reside on the homelands of Indigenous peoples is an important step toward recognizing the history and original stewards of these lands. The intent of land acknowledgement is to extend beyond spoken or written words. It must be implemented thoughtfully and meaningfully and be reinforced by direct support and consideration of Indigenous peoples. As we gather, we honor and acknowledge that the University of Colorado's 4 campuses are on the traditional territories and ancestral homelands of the Cheyenne, Arapaho, Ute, Apache, Comanche, Kiowa, Lakota, Pueblo, and Shoshone nations. Further, we acknowledge the 48 contemporary tribal nations historically tied to the lands that comprise what we now call Colorado. Acknowledging that we live in the homelands of Indigenous peoples recognizes the original stewards of these lands and their legacies. With this land acknowledgement, we celebrate the many contributions of Native peoples and also recognize the sophisticated and intricate knowledge systems Indigenous peoples have developed in relationship to their lands. With that, I will turn things over to Rachel, who will be introducing our speaker.
Thank you. Hi, everyone. My name is Rachel Adams, and I'm a research associate at the Natural Hazards Center and the National Science Foundation supported Converge initiative. So today, during this IBS webinar, we will be hearing from Sabine Loos, who is a U.S. Geological Survey Mendenhall Fellow in collaboration with the Natural Hazards Center. She applies risk analysis, statistical learning, and user-centered design techniques to develop tools that inform effective and equitable disaster risk reduction and recovery. Through the lens of data, her work bridges engineering with the natural and social sciences to support the most vulnerable. She has worked across Nepal, Singapore, and New Zealand to gain firsthand experience of the impacts from disasters. The transdisciplinary nature of her work has led her to collaborate with Kathmandu Living Labs, the World Bank, NASA JPL, Humanitarian OpenStreetMap, and others. She also has co-chaired the 2020 and the 2021 Natural Hazards Researchers Meeting and co-hosts the Risk and Resilience Data-Rathon. She is a recipient of the John A. Bloom Fellowship in Earthquake Engineering and the National Science Foundation Graduate Research Fellowship. She holds a PhD and master's degree from Stanford University and a bachelor degree in civil engineering from Ohio State University. Welcome, Sabine.
Thank you, Rachel. That was a lovely introduction, and it's always a little strange to hear yourself and all of your accolades being introduced, but let me just share my slides, and hopefully I can get a thumbs up that you can hear me and see my slides. Okay, great, awesome. Well, hello everyone. Thank you so much for having me here today. My name is Sabine Loos, and I am super excited to be sharing with you my research on data for disasters, designing user-centered and integrated earthquake information. And just so you have a little bit more background on me, and so you can have a sense of how I got into researching disaster data, really, I'm an engineer by training, and I really kind of respect and love all of the disciplines that work in the natural hazard space. And in fact, I'll be joining the Civil and Environmental Engineering Department at University of Michigan, working on incorporating the human habitat experience into engineering curriculum, because really, I've been understanding and interested in how our designs interact with the world around it. And now I've mostly worked on disaster information in many places around the world, thinking about how to prepare for or recover from recent earthquakes. Right now, like Rachel mentioned, I'm a Mendenhall Fellow with the United States Geological Survey, or USGS for short, and I'm currently working in collaboration with the Natural Hazards Center. And so for those of you who aren't super familiar with the USGS, I've included our mission statement here. And really kind of our mission at the USGS is to provide actionable intelligence, aka information, on the way humans and natural Earth systems interact. And so I'm in the Golden Office down at the School of Mines, and we mostly focus on earthquake hazards and landslide hazards. So hopefully you can see from this mission of the USGS that our job is essentially to provide information or data. And this is really awesome because we can provide information that many people look to around the world when an earthquake happens and need to figure out what's going on. And that's essentially the job of many engineers and natural scientists. Many of us are in the business of developing methods to make data. This is definitely the case, as you can see here, from natural hazards and risk information. However, not many of us are trained in how to critically think about how we develop this data, who we design it for, and what impacts this data might have in the long run. And we're starting to, don't get me wrong. And so natural hazards related data really does have an impact. And to provide a brief example, let's go back to the Nepal earthquake. And you're going to hear me talk about the Nepal earthquake quite a lot. And that earthquake occurred in 2015 and affected hundreds and thousands of people in Nepal. This was, of course, a very devastating event, and I don't want to minimize that, but it was also super inspiring in terms of the data response. There was so much data produced after this earthquake, it was overwhelming. So we can see there are multiple new technologies being unveiled, like satellite estimates of damage, but also digital humanitarians or volunteers in Nepal and around the globe were contributing their time to map out different places of interest that could be used for anyone who was affected. There were also a lot of response and recovery plans that could have used this data. So many of these early recovery plans that I show here, they aim to make sense of what happened so they can figure out how to allocate shelter or later on aid. For today, let's zoom into this one plan, which is called the Post-Disaster Needs Assessment. And you'll hear me mention this PDNA a lot today. So what the PDNA does is essentially the government of the affected country is trying to identify what their recovery needs are through estimating what the damages are, reconstruction costs are, and what are the population needs. The government of Nepal did this super quickly, and exactly 2 months after the earthquake, they were able to pull this PDNA together. And this PDNA resulted in a pledge of about $4.4 billion in aid from international donors. So hopefully you can see here that the PDNA is a very crucial moment after a disaster. It not only leads to a ton of funding flowing into these countries, but it also serves as a lasting document that memorializes what happens after a disaster. Now, if we dig into the PDNA more, post-disaster needs assessment, the main information that influences that dollar amount is this map. And this is the map of the impact to the different districts in Nepal. And so you can see here that the most impacted districts are those shown in the middle in darker orange. And there are a few things that I'd like to highlight about this map. One is because the PDNA is produced relatively quickly in just 2 months after an earthquake, and they have a very standardized process. A lot of the data that I mentioned earlier that was collected by folks on the ground or through satellites did actually not inform the numbers in this map, and partly because this really new and emerging technology has not yet been designed for these specific uses. Beyond that, what did go into this map of impact were estimates of housing damage and associated loss based on the value of the house. Therefore, this map quantitatively takes into account only the shaking intensity, mainly from seismology, and the damage to buildings, mainly from civil engineering. Now, this map went on to have lasting effects, which I'll discuss in more detail later. It really framed how the recovery took place in Nepal for years after the earthquake, with various organizations reproducing this map to help them plan out how they were going to work on the recovery. And as you can see from the map on the right, which is the map of the concentration of non-governmental organizations working on the recovery 4 years after the earthquake, a lot of the assistance was concentrated in these areas of high damage, rather than those other districts that might have had pre-existing issues that would make it challenging to recover. Now, really, this is no fault of Nepal's. Their post-disaster needs assessment process was actually a massive success, and that brought together so many different groups in Nepal to plan for the recovery together. It's just kind of a fact of the way that we measure and evaluate disasters, and that we tend to focus on very traditional methods and very easy to measure metrics, things that we can see like housing damage. This is what happens everywhere around the world, right? So an example that might resonate here is kind of the main way we prioritize disaster funding is through insurance, which is based on disaster damage and losses. So what I'm trying to say is that, yeah, disaster data has a ton of opportunities in that we can increase situational awareness in a lot of places around the world. But there are some challenges with designing it thoughtfully and effectively. One is that a lot of these emerging data sources from remote sensing or citizen science, they're currently not designed for these specific uses, and that leaves them unused for very influential and long-standing decisions. The second is that a lot of our existing disaster data tends to focus only on the natural and the built environment. And I'm not saying that's bad, but it does tend to lead to decisions that emphasize rebuilding structural safety rather than also addressing issues of longstanding vulnerability. On the flip side, when we look at the decisions that are increasingly being driven by data, right, we don't fully understand their ramifications. And this leads us to repeating the same way of measuring and implementing actions before and after every disaster. So with this in mind, I asked, how can we design user-centered and integrated data for hopefully more effective and equitable decision-making? And I'll go through this with 3 main areas. One is designing user-centered data or understanding the uses of data before the design process. The second is integrated data development, or trying to incorporate factors from all of the disciplines that work to understand natural hazards into the data design. And then third is effective and equitable decisions. So really analyzing the outcomes of data-driven disaster decisions for how effective they are and how they might reduce disaster-caused inequities. And I'll explain this with 3 areas of work. One is user-centered damage data. The second is integrated non-recovery data. And the third is analyzing the effects of damage-driven recovery policies. All right, so the first one, how can we design user-centered damage data? And so taking a step back here, what does user-centered mean? So typically what happens when we design a product or we design data is that scientists and engineers develop a product based on what they think is needed and what is scientifically possible. Then they might put that out in the world, and then maybe that data or product makes its way into someone's hands who might use it on the ground. A more user-centered approach, however, we'd first ask users what their needs are, then we'd develop a product with those needs in mind, and then hopefully get feedback and iterate through that design. And so I'll go through this process with building damage information. And so like I mentioned before, building damage information is a very common disaster data type. It can come in the form of detecting damage in satellite imagery, that's pretty new, but also assessing damage through field surveys on the ground, which engineers have been doing for ages, or rapidly forecasting damage using risk models. But we actually, until very recently, didn't really understand why response and recovery stakeholders might need this damage information. And so a team of us actually went about trying to figure this out. And we interviewed 11 response and recovery stakeholders who had experience with international disasters and also whose work involved building damage information. And what we found was that there are really kind of 6 key tasks that rely on building damage data. And you could organize those by spatial resolution on the y-axis and time that that task was carried out on the x-axis. And so spatial resolution means, do you need that building damage information at the building level, or do you need it for entire region? And so if we kind of zoom into one of these tasks, again, I'll focus on the post-disaster needs assessment. Damage information here is needed at the regional level and in a fairly quick turnaround from 6 weeks to 2 months after an earthquake happens. So kind of very specific information that's needed very quickly. And so we aim to understand these uses so we could better design damage information to kind of inform these uses, right? And so we focused on the post-disaster needs assessment to design a damage estimation approach that uses the multiple data sources on building damage that are available in that time period to estimate damage at a regional level. And so what do I mean by the multiple damage data sets that are available? If we look again, instead of tasks that depend on damage data, the sources of damage data, we can see that many data sets are actually available within time for the post-disaster needs assessment. But a lot of these, like I mentioned before, are not currently being designed for this use. And that's because they're too inaccurate or uninterpretable. And so what I mean by that is that, one, here's an example of a forecast of building damage. And this is an inaccurate estimate of damage, not accurate enough for things like the post-disaster needs assessment, because essentially we're predicting the average damage at all locations because we have very low resolution information here around Nepal and around Kathmandu. On the other hand, we have these satellite-based estimates of damage. And these, as you can see here, are a little bit more specific. You can see a granularity of damage. However, the metric is uninterpretable. So we know that the number 255 means high amounts of damage and 0 means low amounts, but we don't know exactly how those map to damage on the ground. And so this is a useful piece of information, but it's less interpretable, right? And so on the flip side, outside of those, what we call secondary sources of damage information, we have more accurate data like field surveys, which are carried out in small areas after an earthquake happens, but they cover a smaller region. So our idea is, what if we can calibrate all of the secondary data from remote sensing or forecasts with a small sample of field surveys to then estimate damage in time to support decisions like the post-disaster needs assessment. And so what we do is we apply a method called regression printing, and I'll kind of zoom through that here in the next few slides. And we apply that method using a hypothetical set of 100 field surveys as shown on the left, and combine those 100 field surveys with real secondary data on damage as shown on the right from the Nepal earthquake. And the way that this method works is that we can estimate kind of the average damage over space by developing a regression function. And then we estimate the stochastic and spatially correlated residuals around that trend using a method called kriging. And the final damage estimate is simply the sum of those two parts. And now the neat thing about this approach to estimating damage is we can then make use of all of that damage data that was super valuable and produced after the earthquake, from forecasts to satellite-based estimates to even crowdsourcing. And the estimated damage, as shown to the left from this method, is very similar, as you can see visually, to the true damage. The main difference is the map on the left could have been produced in a few weeks after the earthquake, whereas the map on the right took about 1.5 years to develop because it required people going to hundreds and thousands of buildings and surveying the damage there. We can also see that the estimated damage is more accurate than any of the input data sets. And so because we designed this approach to be flexible to multiple inputs, multiple types of data that might become available in the future, we wanted to test this to make sure that would work in multiple different areas, especially if things like the PDNA or insurance was being implemented elsewhere. And so we applied this method to 3 other recent earthquakes, all which had very different patterns of damage, but also qualities of input data. And we found that the accuracy of this method can change depending on the field survey sample. So here's the distribution of an error metric called the mean squared error of the damage estimate from our approach when we use different field survey sample realizations in Haiti. And the lower the mean squared error, closer to the left is more accurate. And so you can see that in Haiti, this method is more accurate than any other damage estimate that would be available in time for the post-disaster needs assessment. But also the same can be said for New Zealand and Italy, and of course, Nepal as well. So this is just one example of how we designed a data development approach that was meant to inform one specific use case. But hopefully right now, you're starting to see why are there all these sources of damage data and why are many of them being unused for the tasks that we identified at the beginning of this section. And hopefully by now you'll notice I've included a timeline of both the time of availability of different sources of damage, whether they be forecasts or surveys, but we've also identified the timeline of tasks that depend on damage data. And that was through our interviews at the beginning. And so if we simply merge the two and see how they line up, as you can see here, the damage data sources, so the forecast is the remote sensing on the top, a lot of them are available in time to inform a specific use on the bottom. However, like I mentioned before, many of these data sources on the top aren't actually informing many of the uses on the bottom, or we just don't have a good understanding of that. And there are both very practical and ethical issues of collecting and producing data that goes unused after these disasters. Of course, the practical is that there's a ton of time, energy, let alone money that goes into making this data that's not fully utilized. But there's an ethical issue is if the process of data collection and observation with things like satellite imagery, that can be quite extractive if it doesn't then go on to support local risk reduction or recovery planning. So currently, this is current work, so it's still in process. We're evaluating how these damage data sources are used and if they're used for these outlined tasks. And we're doing this by performing a systematic review of reconnaissance reports, literature, media emails, what have you, and evaluating how these different damage data sources were used after the events that I introduced earlier. So for example, again, looking at the Nepal earthquake, the forecasts, so things that kind of show the rapid shaking, they were used for situational awareness and also aid requests like the post-disaster needs assessment. On the other hand, more of the satellite-derived or remote sensing-derived estimates were mostly used to plan for more data collection by other scientists and later on published in academic journals for scientific understanding. And so we continued this analysis for all of the damage data sources that existed in Nepal, and then for all of the events we studied. And so this is a lot here, and I'll just highlight a few key takeaways that we're finding right now. So far, what we can see is that a lot of this damage data really does largely inform scientific understanding. Though few, like recovery-oriented surveys, and I wish I had my pointer here, consistently informed recovery allocation and simultaneously informed scientific understanding. And so this highlights the importance of user-centered design of disaster data. If we know ahead of time what the use of our data is from the start, before we start developing methods and collecting it, we can design it in such a way that it simultaneously informs local planning, but also informs scientific understanding instead of one or the other. So in summary, we started off with a study to understand the uses of damage information. Then I went into an example of how we design damage information for a specific use. And then I closed with current work on how we're evaluating the uses of overall existing damage data sources. And I'm kind of tired of talking about damage data. And like I said, disaster impacts are much more than building damage and losses. And to show an example of both user-centered and integrated data development, I'll walk through our model of non-recovery information. So again, taking a step back here, I want to just kind of do a definition check of disaster recovery. And I want to point out that recovery is very multidimensional, and it can happen at many units of analysis, whether it be the individual, the household, or the community, over many areas of life. And we fully acknowledge, our research team, that physical reconstruction is only one component of housing recovery, though we will use reconstruction as our recovery outcome of interest to illustrate the development of a non-recovery model. And so now when we talk about disaster impact and recovery, we can conceptualize it using this thing called the recovery curve. And so what the recovery curve does, it relates some metric of well-being on the y-axis. And here I use housing condition again as a starting point, with time on the x-axis. And when the disaster occurs, a house will be damaged. So that's what we just estimated, but it's also important to consider the ability of that household to recover or reach a sense of normalcy over time. Importantly, not all recovery curves look the same. So an average household might be damaged and then over time be able to recover, like the curve I show on the left. But a more vulnerable household might stay in that impacted state and not be able to recover. And this is what exacerbates inequality after a disaster, or just part of what exacerbates that. And so in talking to many non-governmental organizations and agencies and groups involved with reconstruction after the Nepal earthquake, I found that a lot of folks wanted to know who were these groups on the right that might not recover and where were they? And so one might think, when we think about a data set that gets at the differences in vulnerability, we might think of a social vulnerability index. And so this is what I show here. And I just like to point out that this is an example of how inequities exist even in data, because there were some issues in applying this index into Nepal, because essentially what this does, it's a weighted average of multiple factors that relate to vulnerability. And they really typically don't exist much outside of the US or Europe, because they mainly rely on census data, which isn't fully available in a lot of places around the world. Beyond that, again, when talking to a lot of folks who are working on the recovery in Nepal, they understood vulnerability to be that lack of recovery or the inability to recover, rather than this high, medium, and low index. And so that's fine. As an alternative, we also looked at other spatial models for socioeconomic indicators. So for example, researchers have been using open geospatial data to estimate things like under 5 mortality rates or different poverty indicators. And these are a little bit more suitable for many countries around the world. And so what we aim to do was combine these two ideas to estimate the spatial distribution of non-recovery. And again, non-recovery is that practical understanding of social vulnerability. Which of those households would struggle with completing reconstruction due to both physical factors, but also social, economic, and geographic reasons? And the data we use to predict non-recovery is actually from a questionnaire on monitoring impacts and recovery after the 2015 Nepal earthquake. And so this was a survey completed about 5 years after the event by the Asia Foundation for over 3,000 households. And one question in that questionnaire asked about reconstruction progress, which we model as a binary outcome, reconstructed or not. And essentially, we are aiming to predict the spatial distribution of non-recovery at all of those locations that haven't been surveyed on the right. And the way that we want to predict this is by using a set of what we compiled 31 potential predictors. And compiling these predictors, we drew from theory on vulnerability and resilience and development, but also making sure, importantly, that this data that we use could be available in most countries after an earthquake happens. And then similar to our damage estimation approach, we compile these predictors with our field survey data, develop a model for non-recovery, and use that model to predict the probability of non-recovery throughout space. And specifically, the model we use is a random forest model, and I'm happy to go into that in more detail if anyone has questions. And as you can see here, the final map of non-recovery on the left can hopefully be used as an additional estimate of post-disaster needs. So stakeholders planning for early recovery can consider in tandem which areas are most damaged, right? But also which areas are the least likely to recover due to these factors. And really nice about this is that we can see what predictors are most related to non-recovery. And so we found 8 data sets that were most predictive of the lack of recovery in Nepal specifically. And we categorized those into 3 groups: hazard exposure, reconstruction complexity, and rural accessibility and poverty. And we can also look at the influence of each of these predictors on non-recovery, which is bound in our model. And so I know this is a lot here, and I'll just kind of explain this further with 2 variables. And so what this plot shows is the relationship found between non-recovery and the variable of interest in our model on the x-axis. In this case, I'm showing remoteness. And each one of these lines is the relationship found between remoteness and non-recovery for one household in the training data set, if we were to vary that value of that variable across its entire range. Now, the dark line is the average relationship found in the model over all households in our training data set. So what this plot shows specifically is that households that are more remote are less likely to recover. Now, this variable in relationship is on remoteness. And this is interesting because the model identified very Nepali specific factors for non-recovery. So remoteness might only be specific or true for Nepal, which you can see from these pictures is a very mountainous and remote region. So in the picture on the left, this is one of our field researchers, and they're climbing a mountain to reach one of the villages we surveyed. And as you can see from the picture on the right, one of those villages is indeed nestled pretty deep in the Himalayas and hard to reach by car. And so what we found is that it was harder to get materials to a lot of these villages or even technical assistance, and that did impact reconstruction. We also found that the higher the food poverty prevalence in an area, the less likely these areas were to finish reconstruction. And again, we saw this in many of our interviews where in certain districts that were damaged, they also faced many pre-existing issues with long-term risks to overall health, like food poverty. So here is a person in a village we visited going through his recent catch for the day, and you can see that it is quite empty. So hopefully by highlighting these 2 variables, you can see by incorporating kind of more socioeconomic and geographic variables into our model of non-recovery, we can start to see how chronic issues of poverty and vulnerability do in fact relate to the ability to recover. And therefore, we do have substantial data that supports acting on these longstanding issues as part of an early recovery plan. So as a review here, I introduced a method to estimate the populations that might have challenges during reconstruction and the potential factors associated with that. And the aim of this model is really to promote more holistic and context-specific post-disaster information beyond building damage. And so there were 2 main benefits of this model, and that it could highlight very Nepali specific factors and also longer term risks to overall health. And in the future, I hope to work on this with new metrics and data sources on things like population displacement and other hazards. And then finally, I've just spent kind of the majority of the presentation introducing 2 ways to design user-centered and integrated data. But let's think about what that is going on the decision side. Do we know the impacts of these decisions that are increasingly being driven by certain types of data? And to go through this, I'll run through the effects of damage-driven recovery policies. So as background, Nepal's recovery policy really focused on this idea of building back better. And this is an idea that's been around for a while, and it's with great intention. The idea is to rebuild houses and structures more safely that they might better withstand future disasters. And the way that Nepal did this was by treating all households as equal and giving each the same amount of money based on building damage, and therefore designating a certain set of designs those houses could use that money to rebuild. And I know that we're probably aware of these definition checks, but I just wanted to relate equality and equity to Nepal's reconstruction policy. So Nepal's policy really treated all households as equal, which is good. It's similar to giving everyone the same height ladder in this picture, no matter their height and ability to reach an apple. But a more equitable recovery policy could have considered different amounts of aids or additional help, such as this picture on the bottom left with different size ladders to households depending on their pre-existing kind of capacities to recover. And so one project where we're starting to look at the multiple different effects of the reconstruction policy is using that same data set I used to model non-recovery. And here, one of my undergraduate students, Jenny Levitt, has organized this data set, which is actually longitudinal in nature, to look at household level trends over time in reconstruction progress. And using this data, we've been able to build household recovery trajectories. And what we found so far is that, in fact, Nepal's recovery policy has been working. Those have received aid have recovered more quickly. However, some populations are being left behind, such as older populations. And again, this is really preliminary work, but I've also been part of a separate project with many different researchers from Switzerland, Nepal, and Singapore, and we've collected a separate set of interviews and data on the effects of building back better. And so here you can see, if you zoom in really quickly, our partners, Kathmandu Living Lab, are training the field researchers on that recovery curve before they go into the field. And again, with this research, we found that the policy is working as intended. Many houses are in fact rebuilding with safer materials. So they started with stone with mud mortar, and now they're building with things like brick and cement mortar. But there have been some unintended costs, such as many of these households have gone into increased debt to fund these safer homes, which have also ended up being smaller. And so this just kind of highlights the complex trade-off that households have to make building back better. Do we want these households to build back better so they're safer from future earthquakes? Or do we want them to kind of lose some of that safety net that would protect them from their day-to-day or non-earthquake events, such as the COVID-19 pandemic? And so hopefully from these two smaller studies, you can see how it's important to study the effects of data-driven disasters decisions so we can continuously improve in how we prepare for and respond to earthquakes in the future. So looking to the future, how can we continue to design user-centered and integrated earthquake data that is more widely available? And part of this is our current research at the United States Geological Survey. So as I mentioned at the beginning of this presentation, the USGS has developed multiple products that since the 90s, essentially, which really provide a ton of information on what is happening in the minutes to hours after an event. So many people around the world look to the USGS to understand, where's the shaking, what's the magnitude? And then there are also many very influential users such as FEMA or USAID and more. While a ton of progress has been made in developing this kind of suite of products, again, these products kind of stop short, and the closest we get to human impacts are damages and deaths. And so what we're hoping to design is a next generation product that is more human-driven and user-centered, and it goes beyond these very kind of equal metrics to acknowledge the inequities that are caused by earthquakes. So the approach that we're taking is very similar to the work I've just presented. Again, we're starting with users and identifying their informational needs. And specifically, we're going to prioritize those users who are innovators in the equity and disaster risk reduction space. whether they be community-based networks or very influential organizations that do have the agency to affect change regarding disaster inequities. And then taking their informational needs, we'll design kind of a human-centered loss product and hopefully continue iterating this design with interested users. And so hopefully by now you've seen that the work I've presented today is really taking this cycle of users and data design. And really what I'm hoping to do with this work is designing disaster data that really works towards achieving disaster justice. And so one part of that is designing data that aims to reduce vulnerability or the unequal distribution of pre-disaster risk. The second is working towards distributive justice or addressing the unequal distribution of post-disaster resources. And finally, thinking about procedural justice. And this is really thinking about how we can conduct our data design, whose information and needs we're prioritizing, and how we're communicating. So the way that I like to frame that is thinking about who is at the table, who are we including in designing our data, who are we asking about their decisions, and how are we choosing to communicate with our users. So in the project in Nepal, we really aimed to design data with a group that was from multiple disciplines and identities. So we had a very transdisciplinary team designing these solutions, from engineers to science and technology studies. And we also had a really diverse team with multiple age groups and from all different places around the world. And a lot of times we didn't really agree on many things, but what we could come back to was that we agreed on our same basic mission and our values in this work. And so we were also very intentional in how we shared our research. So we tried to prioritize communicating with multiple audiences, making our data in code so those on the ground could actually use it. And we also aimed to use multiple formats of communication. So of course we had academic publications. We also published blogs, reports, and visualizations. And in fact, to increase the use of data visualization specifically, which has proven to be really accessible in Nepal and also around the world, Arogya Kairala, Yolanda Lin, and I've created this community called the DAT Artathon, which is a group of data visualizers and artists in the natural hazard space. And so every year we bring together around 10 to 15 DAT artists from around the world, and we kind of train each other and support each other in making natural hazards risk data that is more understood and accessible by many. And to find out more about the DAT Artathon, I really encourage you to visit our website. And then kind of speaking about community, I'd like to close and acknowledge the small community it took to conduct this research, as well as our many funders on the right. And most importantly, I also want to close bringing back up this picture, remembering that each one of these lines in this graph is a household. And so it's important to remember when working with this data, it's easy to forget that each data point was a lived experience by a family, a person that was affected by a disaster. So I want to take a moment to thank the many survivors who responded to these questionnaires and the surveys presented in this work. And while not nearly enough, hopefully this research helps to promote better approaches to disasters in the future. And with that, I am happy to take any questions, and I'll also give a small plug that I'm currently hiring 2 interns. If anyone is interested, they can reach out to me.
I see that Jennifer Tobin has her hand raised. If you want to go ahead and ask her question.
Sure. Hi, Sabine. What a wonderful presentation. Thank you so much for presenting that awesome research. I was wondering if you could talk to us a little bit more about how, when you presented your data back to the communities, or any of the communities you use as examples there, how it was received and how they could imagine getting that data more quickly so that it could inform their initial reports. And like, who would they even reach out to begin that process if they didn't already have the, the ability to collect the data themselves and such?
Yeah, that's a really great question. And I will admit that we had bigger plans to kind of address this idea of reciprocity, or kind of sharing our research back with the communities, though COVID kind of hampered a lot of the workshops and trainings we were hoping to do. Right before COVID, though, we did meet with the National Reconstruction Authority of Nepal, who would be the group or the disaster management agency in Nepal who would be kind of implementing some of these tools to share back. But yeah, I think there's a lot more to be done in terms of maybe even not specifically related to the results of this, but just kind of building capacity to be able to kind of run and work with these tools, or just understand the results of these tools in the specific remote communities that we worked in. And unfortunately, COVID hampered some of those plans. But yeah, I would love to talk with folks in the Natural Hazard Center on their ideas there, because I do have a few good contacts that are working in these communities that would help kind of creating that relationship. Hopefully that answers some of the questions.
Yeah, thank you.
I see now that Nania, you have your hand up as well. So you want to go ahead and ask Sabine a question?
Great, wonderful presentation, Sabine. I really appreciate it. Super interesting. And I was wondering if you could elaborate a little bit more on how you go about identifying equity innovators and the process for reaching out to them.
Yeah, so that's kind of currently what we're working on now. My current supervisors, Lori Peak, and two supervisors at the USGS. And so the way that we're doing that, and I'm welcome again to suggestions, is we currently have like a listserv of all of our users of our current earthquake products. And so importantly, I had grand dreams to expand our user base so that it would get to more, but it would kind of take a lot to explain USGS and products in general. So we're going to focus on our USGS users already, and then specifically those users that, again, the term we're using is equity innovators, or another term that was thrown around was disaster influencers. So again, those agencies that have the influence. So it kind of goes twofold. So some of those groups are, if I go to their website and I see in their mission statement that they mention something about kind of prioritizing marginalized or underrepresented groups in disasters, or if they have a very kind of equity related program that is aimed at kind of reducing these disaster-based inequities, I'll include them on the list. But then again, there's also kind of these disaster influencers that have a lot of agency, for example, like FEMA. And there's like small groups within FEMA that are creating like more equity related programs. And I'll focus on those specific users, because if FEMA gets on board with something like that, then that will have a lot of influence. But yeah, again, very interested in taking advice or kind of your thoughts on that, because I know there was a lot of work on doing that with the Haywired research as well.
Yeah, that's kind of why I was asking, and I think it would definitely be interesting to get together and talk about that.
Yeah, for sure. I love that presentation on kind of the work that the BAF fellows or BAF was doing to promote the Haywired research. Awesome. Well, this is great. Thank you for the lovely questions. And it's kind of nice to see everyone here. And even though I can't come to the Natural Hazard Center in person a lot of the times, happy to connect whenever.
Wonderful. Thank you, everyone, so much. Are there any last minute questions, or you're welcome to stay around, stick around if you'd like to. Thank you. All right. Thank you so much.
No problem. Thanks, Cindy, for setting everything up.
My pleasure.